Let's talk now about covariance. Covariance is the way that two sets of data move relative to one another. So there's our formula, x minus x bar, which you take each one away from the mean, and same with the y values, you take each one away from the mean, divide by the total number of data sets, and this is your covariance. Okay, let's see how that works in practice. We've got these two sets of values, and we want to know how they move relative to each other. And that is the covariance, which is measured. Now you know that we've already found the mean and the variance of each lot. I won't go through that again. I'll just use the formula from Excel. So we're going to use the equals the average. Just a lazy way of finding the mean. So it's the average of these particular numbers here. And then I'll close up the bracket and press enter, and that should give us the mean, which is 2. And I'll just drag that across because the mean of these other numbers is 4.5. I'll just make that area red so that we can they'll stand out. Now the variance, if you could remember how we did it, we subtracted each one from the mean, squared them, added them up and divided by 3, but I'll use an Excel formula. It's a bit deceiving actually. The formula is var-p, not var, and that's because, well, it's because it's the variance of, never mind, it's just the one that we use. So that finds the variance of that set of numbers, and I'll just drag it across, and that's the variance of y set of numbers. I'll just bring those decimal places down a little bit to make it a bit tidier. Okay, now what we need to do now is to subtract the means, the values of x from the mean. So it's x minus x bar, and then I'm going to take y minus y bar as well. Y minus y bar. So let's see how we do that. We can just take equals. In this case, we're going to have an equal sign. We're going to take the value of x and subtract the mean, which is this one. Don't forget the F4 key to give you absolute reference, and then we can simply drag those down. And then we can do the same for the y. I think I can drag this formula across. That looks pretty good. So that's the value of y, subtract, the mean of y. So I'll drag that across, and that formula should be okay now. So in other words, 3 minus 4.5 is minus 1.5. And then I need to just drag those down and do the same with the other. So what I'll do now is to add these up and use the auto sum. I'll double click, and then I'll no, this is wrong. I need to multiply these together first, sorry. So delete that, and I'll call it the product, P-R-O-D for product. Let's multiply them together, so we'll say equals this, and then we multiply by this, and then tick, and then drag them down, and then we take the actual sum of all those, so auto sum, and it comes to a total of 4. And finally, we need to divide this number, divide by the number of pairs of numbers. We have 3 pairs of numbers, so that should give us the covariance of the set of numbers, an indication of how these numbers move together. So just checking our formula, I've got the covariance is the sum of the deviations from the mean in both cases, summed, and then divided by the total number of pairs. So let's see how we might calculate the variance of these two sets of data using Matlab. So what I might do is just make a new script and call that whatever, save it as test or something like this, a test covariance, and then save that. And now I always like to put a CLC in there to clear the screen. You don't have to do that. So now we've got our 2 data sets, and I'll call them x and y. So x is equal to that data set, which is 1, 2, and 3. And then I don't need to echo those to the screen, so I'll put a semicolon there. If I copy that down and change that to y, and the y values are, we've got 3, 3.5, 3.5, and 7. Okay, so we can now take the mean of each of those. So we can say the mean mean of x is equal to indeed the mean of x. And similarly, we can say the mean of y is indeed the mean of our y array. So we can run that to make sure that we've got the right values of 2 and 4.5 for the mean. So all is well so far. Now we need to subtract each of the values of x, subtract them from the mean of x, and similarly we subtract the y, subtract the mean of y. Then I'm going to multiply them together, but we need to be careful how we multiply them together because it's going to be element-wise. So we want to multiply them together, and what will I call it? So I'll call it just C for the moment. C for covariance is equal to. Now, when I multiply them together, I've got to be careful because I'm multiplying them element-wise. So I need a dot in here to multiply them element-wise. We might as well just see. I'll just stop the echo for those two, and then I'll try and run it to see if that's working. Let's take a look. We've got 1.50 and 2.5 as we just saw. 1.50, 2.5 here. Now we need to finally then multiply. So remember we needed to add up the numbers, so I'll do that by using the sum formula, and I'll press the end key, take me to the end where out here looking, and that should give me the sum. I could run that to check that value, which is the sum of all those, which is 4, which is equivalent to the sum of those. Now, okay, so we finally therefore need to divide the whole lot, divide by the total number of pairs, which we know is 3.0. And let's see what happens when we run that. We get a value of, if I can find it down, of 1.33, which indeed is the same answer that we got for the variance using Excel. While I'm here, I might as well make a graph of the values. So if I highlight them, and then I can take, let's see, insert a chart. We want an X scatter, believe it or not. It's a scatter. And you can see how the values are plotted. Just the X along this axis and Y on that axis. We could actually put a trend line. Perhaps I'll do that later. But for the moment, you can see how they're sort of moving, how they do move relative to one another. And so we've got a value of 1.33 for this covariance. There is a problem with that, and it's a relative number. That is to say, if these figures were like 100 times bigger, this would actually be 10,000 times bigger. But we need some way of standardizing this value for similar sets of data, and we'll do that when we consider correlation, the correlation coefficient, the product moment correlation coefficient, which we'll talk about next session.